5. Okay, everybody sees that, right, guys? You can count 5 sticks coming out of it. That's easy. If I was to ask you what the degree of A was, in fact, didn't we already answer that a little bit earlier? The degree of vertex A would be equal to 4, because there's 4 edges that are incident upon it. Okay. By the way, it is possible for a vertex to have 0 degree. You can't have negative, and it has to be a whole number value. Okay.
Would it be 0 degree if you just like put the vertex
Yeah.
somewhere?
Like for instance, if I had a graph that looked like this.
Right.
And this was V1, V2, V3.
Is V3 just like arbitrary in this case or something? Because like, does it actually have any significance if it's just kind
If you think of it like the example that I gave before where you have like cups to a string, that's just a cup lying out somewhere. It's still a cup. It's basically a computer that's not hooked up to any sort of connection, if you would. Okay? So those are 2 examples to where that you could see in real life that maybe these 2 computers are hooked up to a network. They can talk to each other. This one's not hooked up yet. It has the capability to be hooked up, but not quite yet. Okay? All right. Let's see, what do we want? Part F. Okay, we need the degree of the entire graph. Okay.
So never put a vertex labeled G.
Correct, because then that's a redefinition of G, isn't it? Just like any other variable. You never want to define a variable twice. Okay? Well, you don't want to if you can avoid it. Okay? So, degree of graph G, okay, is going to be equal to, we know degree of A is 4. Okay. B has degree of 3. We already said C has degree of 5. Okay. D has degree of 2, doesn't it, guys? And then E, I have to scroll up a little bit, sorry, has 4. Okay. So, does everybody understand what I did there? Like, I'm not just pulling numbers out of thin air. I just found the degree of each of the vertices. Okay, so this is degree A, degree B, C, D, E.
I don't understand what degree is.
Okay. How did I get? Okay, let me take a look at that. Okay. There are 1, 2, 3, 4 edges sticking out of it, right? That's how we get degree of A is 4. Okay. If we look at degree of C, 1, 2, 3, 4, 5. There are 5 edges sticking out of that vertex. That's how you find the degree of a vertex. What I did was I did that for all 5 of those vertices. Okay. So if we add this up, 12 and 5 is 17. Or sorry, 12 and 5 is 17 and 6. Wait, what am I adding wrong? Is that?
18.
It's 18.
Yeah.
Yeah. Wait, 4 and 3 is 7. Oh, the whole degree. Okay. Yeah, really. I don't know what I'm thinking. I don't know what I'm not thinking. But
I have no idea what you were doing there.
you know what I was doing? I was doing 4 times 3 plus 5. That's what I was doing. Because I was getting 17 that way. Okay. I need to stick to addition. Okay. Does that make sense, guys? Any questions? Okay, that's the degree of the graph. And then finally, for G, it says to find all edges that are incident upon D and E. Now, when we say that, let's just make it 2 separate problems. So, incident upon E and, let's just put it, and incident upon E. Okay. So basically, incident on D. Okay. That would just be a couple edges, right, guys? If we look at that, we have E1 and E2. Okay, so the only edges that are incident upon D are E sub 1 and E sub 2. Okay. And then if I say incident upon E, you said E has a degree of 4, so we should end up with 4 vertices.
E1, E3,
Yeah,
E4,
E1,
E5.
E3, E4, E5. Okay, so E1, E2, or no, wait, E3, right?
E3, yeah.
E1, E3, E4, E5. Thanks. Okay. So that's the essential terminology of a graph. Okay? So, Michelle?
If you had a graph of just 2, is that of a degree of 2 or it's not a graph?
Yes, that's a good question. Okay? The degree of this graph G would be 2. Every loop contributes 2 to the degree of it, okay? Yeah, even though it's one edge, it still has like the 2 stems sticking out of it.
Oh, from the Bartius.
Yeah, right.
There's still 2 contact points.
Yeah, that's exactly right, or 2 exit points if you would. Okay, good question, Michelle, thank you, ma'am. All right, guys, any other questions I can answer about the basic terminology of graph theory? Okay, really, really easy stuff, right, guys? Okay, so what if I give you guys a scenario to where I ask you to be able to construct a tree, okay, or if it's not possible, to explain why. So let's take a look at some of those types of problems. All right. So I have a graph, and I'll ask you guys to construct this. I have a graph of 3 vertices with degree 1, 2, and 3, okay? Now this is possible, okay? We'll take a look at maybe some that aren't possible later in the course, okay? So if I want to have a graph with 3 vertices, degree 1, 2, and 3, I want you to notice I didn't say it had to be simple. I didn't say it had to be connected. I just said a graph, okay? So when I say just a graph, you do whatever you want with this, okay? So couldn't I do this, guys? Couldn't I draw a vertex here? Draw a vertex here. Okay. Do a loop. And then maybe draw, so that has 3.
You have to go off the first one.
Yeah, we have to go off the first one, like that. Okay. And I think that makes it really nice and easy, doesn't it, guys? Okay. Sometimes what students do is they look at it and they try to think of a simple graph that has to be connected, okay? Unless I specifically say it's simple and it's connected, you don't have to do it that way. Okay, does that make sense to everybody, guys? Any questions?
Oh, 1, 2, and 3, okay, separately, okay.
So this has your degree 1, this has your degree 2, and because of the loop, that has a degree of 3. Okay.
So,
Yeah. That thing that's stemming out is a loop.
so for B, you said they don't have to be simple or connected. You can
Oh,
just-
no. The first one I didn't say simple, right?
Mhm.
For letter B, it says it must be a simple graph. Okay, so that kind of narrows down the possibilities of what you have to work with. Okay, so for B, that one's a little bit tougher. Okay, what I usually do, guys, I just make a graph and I start out with the lowest degree and work my way up, because that way I can try to save the hardest stuff for last. Okay, so this might work. I don't know. So we try this, and then we need something with a 3 in there. So, and we need a 2. So, let's see, what do we think, guys?
Just make a triangle and then have one stick off and just get down to another vertex.
Okay. Like this,
Yeah.
kind of boring, but it works. Looks like a coat hanger. I mean, we're not going for artistic, I guess, integrity here.
So you start with the easiest one, why didn't you just draw the 0, draw the...
Well, this one, oh no, this
Oh,
one.
you're on B, you're B.
Right.
Sorry, I'm on B.
No, that's okay. Yeah. So unfortunately for this one, I think this might be the only way to do it. I want you to notice though, this aren't parallel edges, okay? In other words, you have a vertex in between like these 2 edges, so it's not parallel necessarily. So this has degree 2, 2, 3, 1, which I believe is exactly what we look for. So thanks, John. Okay. Guys, any questions about that one? Okay. For letter C, we have 0, 2, 2, 2, 2, 3, 4. Okay. So I guess the easiest one to draw is the 0, right? So we start with that one. And then 2, 2, 2, 2, 3, 4. So did anyone get that one?
You just draw like a cube,
Okay. So we can draw a cube.
and then have things stem off of that.
Okay. So let's try that. Okay. So that's our 2, 2, 2, 2, and our 0.
Mm-hmm.
Now it has degree 0. And then stem off of that.
Put one in the middle.
Yeah,
Put a
yeah.
dot in the dead middle, connecting this.
So then you connect it with one of the corners,
Okay.
because that creates a 3.
So that's a 3, and this is now a 1. Okay.
We don't need them.
Right.
Right.
I'm just doing what you guys told me to do.
Connect it with the the other
So
3
this
dots.
2 right here?
If you connect it with the other 3 dots,
Okay.
would that become a 4?
Oh, yeah, sure.
But then you'd have
That's a
more
4.
Yeah, then you
Oh,
take
oh,
it
That's
to
a 3.
then you
That's
have
a
one,
3.
two, three.
That's a 3.
Oh, yes.
That doesn't work. It was getting too ugly. So, other suggestions?
Yeah.
Does it, can you just make a line that sticks out and not connect to anything?
Oh no, you have to have it connected to a
Would that
vertex.
technically be a loop anyway?
What's that?
Wouldn't that be a loop, just a line?
Yeah, if it's just a line, it has to, basically if you do this, that's by default, that's what that is. Okay, so yeah, if you just have a line, that's what that is. Scratch that out line, that doesn't exist.
Don't they have a erase function?
They do, but I'm too lazy to pick it up.
It's not on the, you know.
Can I get this one? Man, this is easy stuff, right? Yes, sir?
Draw the box first.
Okay, I just did that. I'll do it again. You guys are bossy. Okay,
Extend one of those vertices to the right or something.
so like,
Yeah.
okay,
And then will become 1, 2, and from that vertex you can make it, try to do it 4 or something like that. Extend them.
Or connected to the top right dot, so then that also becomes 2, so then you have a 3 and 2.
okay, so this,
So now you have
That's a-
4 2s and 1 3.
okay,
No,
No, cause that's a
the
three.
top left you do
so this is a 3.
Oh,
No, no, no. Instead of connecting it, draw a separate. I mean, like from the, instead of connecting it,
We can't do this. Yeah, it's not.
8 plus
That's
3
an
is
odd
11,
number.
11 plus 3 is 15, 15 is odd, can't be done. Remember handshaking lemma?
You could have just.
Ah.
told-
No, I couldn't do that.
I thought you said we would do that later in the course.
We did, 2 minutes later. Absolutely correct, Ryan. I did not lie to you, okay? Not possible.
Wow, we got later in the course so fast.
Ah,
Now all the testing classes gotta be like that.
you do?
That'd be nice.
What, not possible?
Yeah, so all we gotta do is just.
I don't know if you want that, trust me. Okay, all right, any questions, guys, about being able to construct the graphs, okay? Make sure you add them up first, to ensure that they meet the handshaking theory. Okay, a couple other types of graphs are complete bipartite and complete graphs, okay? A complete graph, case of n, so if you see this case of n, that just means you have a complete graph. It's a simple graph to where each vertex is connected by exactly one edge, okay? So basically, what you can do is you can travel from any one vertex to any other vertex in one traversal, okay? The way I think of a complete graph is, I always go back to this example, like the cups, the telephone, where you have the cups and the wires. Like every person in the class has one cup, and everybody can talk to everybody, no matter what, through one wire, okay? So that's basically the way you think of a complete graph. A complete bipartite graph, which if you have k, m, comma, n, simple graph with 2 sets of vertices, okay? You have a vertex set v's, and then you have a vertex set w, okay? Every vertex in v can go to every vertex in w in one traversal, okay? So if I want to go from v to w, I can get there in one traversal. I cannot go from v to v in one traversal. I can't go from w to w in any one traversal, okay? So basically, v's and w's are connected, v's are not connected, w's are not connected, okay? So that's what a complete bipartite graph is. I'll explain to you guys why you ever want to care about one of those in real life in a few moments, okay? Let's just go ahead and construct these complete
oh, so you cannot
graphs.
connect from V to V, but you can connect from V to W?
You have to connect from v to
To
w,
W,
yes, okay? So v to w is okay, v to v is not okay, w to w is not okay.
Okay.
In one traversal, okay? You could get there in 2, but not 1, okay? All right, for letter N, K3, okay? That means I have 3 vertices. I can get to any one of those 3 vertices in one traversal, okay? So here's K3, pretty boring. Okay, that's what K3 looks like, okay? It's not difficult, but if I start on any vertex, I can go from one vertex to the next in one traversal. I want you to notice there are no parallel edges, there are no loops, okay? By the way, don't confuse a loop with a circuit. Loop means you begin and end on the same vertex in one traversal. Circuit means more than one traversal. We're going to learn about circuits next time, okay? If I was to construct K4, okay, if I drew this, I would be close to K4, but I wouldn't necessarily have it. Okay, so can somebody tell me why that is not K4? What am I missing? Go ahead, James.
Go from corner to corner.
Yeah, the corners are missing, right, guys?
Mhm.
So what we could do is we could just draw a crisscross. Now notice if I draw a crisscross through there, that doesn't create another vertex, okay? Another way you guys could do it is you could do this, right? If you wanted to avoid the crisscross. Because now what I could do is I could go from any one vertex to the next vertex, okay? By the way, traditionally, when I see K4, this is what K4 usually looks like, okay? This is just one way to draw it, or what I put up there. But usually, when I look in textbooks, in graph theory textbooks, it looks a lot better than that. But that's what K4 usually looks like, basically a pyramid, if you would, okay? It's either that or the square, okay? And again, we talked about this term earlier, but these two graphs are isomorphic to one another, okay? We're going to have to prove that next time. We're not going to prove it this time. Okay. Does that make sense as to what a complete graph is, guys? One traversal, no loops, no parallel edges, nothing like that. Okay, simple graph. Okay. All right, guys, let's go ahead and finish up by talking about what K23 looks like. Now, this is a bipartite graph, okay? That means there's two vertices in set V, 3 vertices in set W. Okay, so here's what 2,3 would look like. There's my 2. There's my 3. So let's call this set V, and let's call this set W.